Hello there, and welcome to the Sleepy Space Channel. Here is a sobering truth about the universe. It is so enormous that it cannot be crossed, not by us, not by our fastest machines, and not even by light itself. A beam of light that set out at the very beginning of time would not yet have reached the far side of all we can see, even now, after nearly 14 billion years. And the strangest part is that the distance is still growing, the far galaxies drifting steadily beyond any possible reach. Tonight we will measure that impossible distance, rung by rung, from the moon to the edge of everything. If you find these quiet journeys through the cosmos worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next couple of hours, none of this immense distance is something you need to carry. There is nowhere to travel and nothing to reach. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade gently away behind you. Let's begin. There is a question that sounds simple and turns out to be one of the strangest the mind can ask. How long would it take to cross the universe? The words arrive easily, because crossing is something the body already understands. A person crosses a field, a city, an ocean, and each of these has a near side and a far side. The far side waits patiently to be reached. The mind files the universe on the same shelf as those ordinary journeys, as though it were only a larger field, a wider ocean, a longer road home. Tonight, that quiet assumption comes apart, slowly and without alarm, until what remains is something stranger, and in its own way far more restful. The honest answer to the question is not a single number. It is a ladder of numbers, and each rung stands far above the one below it. The climb up that ladder is the shape of this entire journey. At the bottom are distances the body can almost feel, distances measured in the time it takes light to cross a kitchen or reach the moon. At the top are distances so enormous that no traveler, no machine, and no beam of light could ever cross them, not in the lifetime of a star, and not in the lifetime of the universe itself. Between the bottom and the top lies the whole story, and it is told one calm step at a time. It is worth admitting, at the outset, that the title of tonight's journey carries a small note of the impossible. That is honest. The distance involved really is, in a strict and literal sense, impossible to cross, and the reason why is one of the more sobering facts in all of astronomy. But sobering is not the same as frightening. The impossibility we will arrive at is a quiet one. It does not threaten anyone. It simply describes the shape of the cosmos we happen to live inside, and once it is understood, it settles the mind rather than unsettling it. Two walls stand between any traveler and the far edge of the universe, and almost everything in this journey hangs on these two walls. The first wall is the speed of light. Nothing that carries mass can reach it, and even light itself, the fastest thing there is, turns out to be achingly slow against the scale of the cosmos. The second wall is stranger and more decisive. The space between distant galaxies is itself growing, stretching wider with every passing age, and beyond a certain distance it grows faster than any traveler could ever cross it. The first wall makes the journey long. The second wall makes most of it impossible. The plan for tonight is to walk slowly up to the first wall and then to look past it at the second. We will begin close to home, on rungs of the ladder that feel almost familiar, and we will climb outward through the solar system, past the nearest stars, across our own galaxy, and out among the other galaxies, until the ladder finally tops out at the edge of everything we can see. Along the way, we will measure the climb against the fastest machines human hands have ever built, and then against light itself, and the gap between those two will be one of the quiet surprises of the night. None of this asks anything of the listener except stillness. There is no destination to reach by the end, and no effort required along the way. The universe will not be crossed tonight, and that, as we will find, is precisely the point. So let the body settle, and let the mind loosen its grip on the idea of arriving anywhere. The journey ahead is long in the telling, and endless in the distance, and it is meant to be traveled lying still, with the eyes closed, while the far reaches of the cosmos stay exactly where they have always been. Before asking how long it takes to cross the universe, it helps to be clear about what is actually being crossed. The word universe is used loosely in ordinary speech, but astronomy means something specific by it, and the specific meaning changes the whole question. What can be crossed, even in principle, is only the part of the universe that can be seen, and that part has a precise name. It is called the observable universe, and understanding its true size is the first real step up the ladder. The observable universe is the region from which light has had time to reach us since the universe began. The universe has an age, a little under 14 billion years, and light travels at a fixed speed. Light that set out from too far away has simply not had enough time to arrive yet. So there is a horizon around us, a boundary set not by any wall, but by time itself. Beyond that horizon there is surely more universe, but its light has not reached us, and so it lies outside anything we could observe or visit. A natural first guess would be that this horizon sits about 14 billion light-years away, 1 light-year for every year the universe has existed. That guess is reasonable, and it is wrong, for a beautiful reason. While the light from the most distant regions was traveling toward us, the space it was crossing kept expanding, carrying the galaxies that emitted it ever farther away. The light arrives bearing an old image from a closer time, but the source that sent it has since been swept much farther out. When the full stretch of that expansion is accounted for, the edge of the observable universe lies not 14, but about 46.5 billion light-years away in every direction. That makes the observable universe roughly 93 billion light-years across. The number deserves a moment of quiet because it already breaks the everyday picture. The universe we can see is far wider than its own age in light-years, not because anything moved faster than light, but because the stage itself grew while the light was in transit. This single fact, gently held, is the seed of everything strange that follows. The distances out here are not fixed. They have been growing the entire time, and they are growing still. It also helps to set aside a tempting image. The observable universe is not a container with a wall around it, and we are not standing somewhere inside that container looking toward its edge. The horizon is centered on the observer. Anyone, anywhere in the cosmos, sees their own observable universe spread out around themselves, with their own horizon at the farthest reach of the light that has had time to find them. There is no center and no rim in the ordinary sense. There is only a sphere of old light, with each of us sitting quietly at the middle of our own. Inside that sphere lies an almost uncountable number of galaxies. Careful surveys suggest there are at least hundreds of billions of them, and by some estimates as many as 2 trillion, each one a city of stars holding many billions of suns. They are not scattered at random. On the largest scales, they gather into groups and clusters, and the clusters string together into long filaments and sheets, surrounding enormous and nearly empty spaces. This is the texture of the universe at the grandest scale, a kind of slow foam of light and darkness, and somewhere within one ordinary strand of it sits our galaxy, and within that, one ordinary star, and the small world turning around it. There is one more subtlety worth naming softly, because it will matter later. When we ask how long it takes to cross the universe, we have to decide what crossing even means. Does it mean reaching across the breadth of the observable universe as it is measured right now? Or does it mean chasing the far edge as it continues to recede? These turn out to be very different questions, and the difference between them is where the second wall is hiding. For now, it is enough to hold the size in mind. 93 billion light-years from side to side and growing. That is the thing we have set out to cross. To measure a distance this large, ordinary units fall apart almost at once. Kilometers and miles are built for the surface of a small planet, and they become useless strings of zeros long before the journey leaves the solar system. Astronomy reaches instead for a different kind of ruler, one made not of metal, but of time. The ruler is light, and the distances are measured by how long light takes to cross them. It is the most natural ruler the universe offers, and it carries a quiet meaning of its own, because to measure distance in light is also to measure it in the past. Light is the fastest thing there is. It moves at about 300,000 kilometers every second, a speed that would carry it more than 7 times around the Earth in the time it takes to say the word once. Nothing carrying mass can match it, and nothing of any kind can exceed it. On the human scale, light is effectively instantaneous. Switch on a lamp, and the room fills with light in a time too short for any sense to register. For everything in a single life, on a single world, light arrives the very moment it leaves. The first hint of how the cosmos will humble that speed comes close to home. The distance light travels in 1 second is called a light second, and it is about 300,000 kilometers. The Moon, our nearest neighbor in space, sits a little more than 1 light second away. When the Moon is watched from a hillside, it is seen not quite as it is, but as it was, about 1 1/3 seconds ago. The delay is small, but it is real, and it is the first faint sign that even light takes time, and that to look outward is always to look into the past. Step up 1 rung, and the delay grows. The distance light covers in a minute is a light minute, roughly 18 million kilometers. The sun lies about 8 light minutes away, which means the sunlight warming a face on a summer afternoon left the sun about 8 minutes earlier. If the sun were somehow to wink out, the sky would stay bright for 8 more minutes before the darkness arrived. The sun we see is always a few minutes old. Already the everyday feeling of light as instant has begun to soften into something slower and stranger. Farther out, the unit grows again. The distance light travels in an hour, a light hour, is about 1 billion kilometers. Neptune, the most distant of the major planets, drifts roughly 4 light hours from the Sun. A command sent outward to a spacecraft near Neptune would take 4 hours to arrive, and any answer 4 hours to return, so the simplest exchange would fill the better part of a day. The solar system, which feels enormous from inside it, is in truth only a few light hours wide across its planetary span. Light crosses the entire family of planets in less than half a day. And then the ladder takes its first great step, the one that leaves the solar system behind entirely. The distance light travels in a full year is a light year, and it is about 9.5 trillion kilometers, or nearly 6 trillion miles. The number is already past the point where the mind can hold it as a picture. It is better held as a feeling. A light year is the distance light covers, while a world like ours makes one slow circuit of its star. Everything closer than a light year is, in a sense, still in our own neighborhood. Everything beyond it belongs to the wider cosmos. It is worth pausing on the strange gift hidden in this ruler. Because light takes time to arrive, every distance in the sky is also a reach into the past. The farther a thing lies, the older the light that carries its image. To look at the moon is to look 1 second back. To look at the sun is to look 8 minutes back. To look at the stars is to look years and centuries back. And to look at the farthest galaxies, as we soon will, is to look across nearly the whole age of the universe. The night sky is not a snapshot of the present. It is a slow archive of the past, stacked outward in every direction, and the journey we are about to take climbs straight up through that archive, one rung of light at a time. The journey begins where every real journey into space has begun, within the solar system, and even this first leg is slower than most people imagine. The solar system feels enormous from the inside, and in human terms it is, but it is only the smallest rung on the ladder we are climbing. Measuring how long it takes to cross even this familiar ground gives the first true sense of the scale that lies ahead. The machines we have built are the fastest objects our species has ever made, and still they crawl across our own back garden. The moon is the nearest world, a little more than 1 light second away. The fastest crewed craft ever flown took about 3 days to reach it. 3 days to cross a single light second feels almost reasonable, until the next step is taken and the reasonable feeling falls away. The sun is some 8 light minutes off, and the planets are spread across light hours, and the spacecraft that visit them measure their journeys not in days, but in years. The solar system is the one place where human machines have actually traveled, and even here, the traveling is measured against a lifetime. Consider the outer planets, which sit far beyond the warm inner worlds. A probe sent toward the giant planets spends years simply reaching them. The most famous of these outbound craft took about 2 years to reach the first giant, and more than a decade to pass the last of the major planets before drifting onward into the dark beyond. These were the fastest deep space machines of their age, slipping past the planets one by one across a span of years, and the planets they visited are still, on the scale of tonight's journey, practically next door. The whole planetary solar system, from the Sun out to the orbit of the most distant major planet, is only about 8 light hours across. Light crosses that entire span in less than half a day. A beam of light leaving the Sun passes every planet, every moon, every ring, and reaches the edge of the planetary system before a single morning has fully turned to afternoon. And yet our fastest machines, moving at a tiny fraction of light speed, need more than a decade to make the same crossing. The gap between how fast light travels and how fast we travel is already enormous, and we have not yet left the solar system. It is worth letting that gap settle quietly into place, because it never closes again. From here outward, every distance grows, but the speed of our machines does not. The fastest things we can build move at a few tens of kilometers per second, and that figure stays roughly fixed while the distances climb into the trillions of kilometers and far beyond. The solar system is the last place where human travel times are measured in years rather than in ages. Once the ladder leaves these few light hours behind, the numbers begin their long climb toward the unthinkable. So the first leg ends here, at the outer edge of the planets, with the sun shrunk to a brilliant point behind and the open dark ahead. A traveler standing at this boundary would have crossed the entire span of worlds, every place a human machine has ever reached, and would have come only the smallest distance toward the stars. The solar system, which holds everything familiar, is a single quiet step. The ladder stretches upward from here, and the next rung lies not light hours away, but light years. The solar system does not end cleanly, at the last planet. The Sun's influence reaches much farther than its family of worlds, and the true edge of its domain lies astonishingly far out, in a region so distant that no spacecraft has come close to crossing it. Understanding where the Sun's reach actually ends gives the next rung of the ladder, and it is a long step upward from the planets we have just left behind. Beyond the outermost planet, the Sun's wind of particles keeps blowing outward, carving a great bubble in the thin gas between the stars. This bubble has an outer boundary where the solar wind finally gives way to the medium that fills interstellar space. The fastest outbound probes, after more than 4 decades of flight, have only recently crossed that boundary. They are the first human-made objects to pass beyond the Sun's bubble of wind and into the space between the stars, and even so, they have barely begun to leave the Sun's gravitational reach. Far past that windswept boundary lies something larger and stranger, a great spherical cloud of icy bodies that surrounds the entire solar system. This distant shell is the source of the long-period comets that occasionally fall inward toward the Sun. Its inner edge may begin thousands of times farther from the Sun than the most distant planet, and its outer edge may reach as much as 1 to 1.5 light-years out, perhaps even farther. This shell, held loosely by the Sun's gravity, marks the real outer frontier of the solar system. The scale of that figure deserves a slow moment. The outermost shell of the Sun's domain reaches a meaningful fraction of the way to the nearest star. The planets, by contrast, huddle within a few light hours of the Sun. Almost the entire volume that the Sun governs is not the bright realm of the planets at all, but this enormous, dim, frozen outer shell where the Sun is only the brightest star in a cold sky, and a single slow orbit can take millions of years to complete. The familiar solar system of the planets is a tiny bright knot at the center of something far larger and far emptier. To cross this true solar system, out to the edge of that distant shell, would take our fastest machines tens of thousands of years. A probe leaving today, moving faster than anything we have ever launched, would still be drifting through the outer shell long after every person now alive had been forgotten, long after the languages we speak had changed beyond recognition. And only at the far side of that shell, after all those thousands of years, would the traveler finally pass beyond the Sun's last hold and enter the open gulf between the stars. That gulf is the next great step, and it is where the ladder begins to climb in earnest. Everything so far, the planets, the wind bubble, the frozen outer shell, all of it belongs to the Sun. It is one star's quiet kingdom, and crossing it is the work of millennia. Beyond its edge lies a darkness that belongs to no star at all, and somewhere across that darkness, far ahead, waits the first of the other suns. The solar system, in all its enormous reach, turns out to be only the doorway, and the door opens onto a distance larger still. Across the open dark beyond the Sun's reach lies the first of the other stars, and the distance to it is the first rung of the ladder that truly belongs to the wider cosmos. The nearest star to the Sun is a quiet one, far too faint to draw the eye, and the gap between it and us is the smallest interstellar distance there is. It is also, by any human measure, immense. This single step, from one star to its nearest neighbor, is larger than everything that came before it combined. The nearest star is a dim red dwarf called Proxima Centauri. It lies about 4¼ light-years away, which is to say that its light, faint as it is, takes more than 4 years to reach us. It is the closest member of a small family of stars, the nearest star system to our own, which includes 2 larger suns orbiting each other, and this small red companion drifting in a wide, slow path around them. One of those larger suns is remarkably similar to our own, a near twin, and around the small red dwarf circles, at least one world roughly the size of the Earth. 4¼ light-years is a number worth turning over slowly. It is about 40 trillion kilometers, or some 25 trillion miles. Set against the few light hours of the planetary solar system, it is a leap of a different order entirely. If the distance from the Sun to its farthest planet were shrunk to the width of a single step, the nearest star would still lie far across a wide field. The gap between stars is not a little larger than the gap between planets. It is enormously larger than the mind can picture without a model to lean on. This is the distance an earlier night's journey explored on its own, the reach to the nearest possible neighbor and the long quiet that surrounds it. Tonight, that nearest star is only the first interstellar rung, the smallest step into a far longer climb. It is the closest any other sun will ever be, and it is already so far that our fastest machines could not reach it in 100 lifetimes. The nearest star is not a destination so much as a measuring stick, the first honest sense of how widely the stars are spread. For our fastest probe, the one that has touched about 190 kilometers per second, skimming close to the Sun, the journey to this nearest star would take something like 6,600 years. For the slower, outbound craft, already drifting between the stars, the same trip would take more than 70,000 years if they were even pointed the right way, which they are not. Either way, the first interstellar step alone would outlast every empire that has ever risen and fallen, and at the end of it the traveler would have reached only the nearest of several 100 billion stars in our galaxy. And that is the quiet weight of this rung. The nearest star is the easy case, the gentlest possible version of an interstellar journey, and it is already beyond any reasonable reach. Everything beyond it is farther. The next stars are farther, the far side of the galaxy is much farther, and the other galaxies are farther still, by amounts that make even this immense gap look small. The ladder has reached the first other sun, and it has only just begun. From here, the rungs grow not step by step, but leap by leap, and the next leap carries us out to the scale of the galaxy itself. Standing at the nearest star, it becomes possible to feel something the planets never revealed, which is how empty the space between stars truly is. The solar system, for all its reach, is a place where worlds and moons and rings cluster close enough to visit one another. The space between stars is nothing like that. It is one of the emptiest places there is, and the distances that separate the stars from one another are so large that the stars almost never meet. This emptiness is a quiet theme that runs through the whole journey, and it is worth dwelling on gently here. Within about 16 light-years of the Sun, there are only around 60 stars. 60 suns, scattered through a sphere 32 light-years across, and between them, almost nothing at all. Most of these neighbors are faint red dwarfs, far too dim to see without a telescope, each one separated from the next by light-years of near-perfect emptiness. The night sky, crowded as it looks, is in truth a very thin scattering of distant lights across an enormous dark, and the dark between them is the rule, not the exception. The space between the stars is not entirely empty, but it is close. It holds a thin haze of gas, mostly hydrogen, spread so sparsely that each cubic centimeter contains, on average, about one atom. A breath of ordinary air holds vastly more particles in a single lungful than a long column of interstellar space holds across light-years. No vacuum ever made in any laboratory on Earth comes close to being as empty as the ordinary space between the stars. This is the medium a traveler would cross for year upon year, a darkness so thin it is nearly perfect nothing. Because the stars are so far apart relative to their size, they almost never collide. Even when galaxies meet and pass through one another, as they sometimes do, the stars within them slip past without touching, like two thin clouds of dust drifting through each other with room to spare. A star is a small thing set in an enormous emptiness, and the emptiness keeps the stars from ever crowding. Even at the center of our galaxy, where stars gather most thickly, they remain far enough apart that direct collisions are extraordinarily rare across the whole long life of the galaxy. This emptiness is part of why crossing the cosmos takes so long. The distances are not filled with stepping stones set conveniently close together. They are mostly gulf, with the bright places scattered thin and far between. A journey across the galaxy is not a hop from star to star with short rests in between. It is a long passage through darkness, with the nearest light always years away and the next one beyond it years farther still. The bright points that fill the night sky are islands separated by oceans of empty space, and the oceans are wider than the islands by an amount almost beyond reckoning. There is a strange calm in this emptiness once the mind stops resisting it. The space between the stars is quiet and clean and still, undisturbed for ages at a time. A traveler crossing it would pass through a darkness that has lain almost unchanged since long before the Earth formed, and will lie almost unchanged long after. The emptiness is not hostile so much as indifferent, a long stretch of nothing that asks nothing and offers nothing, simply waiting between the rare and distant lights. And it is across this enormous quiet that the next rung of the ladder must be measured, the rung that carries us from the nearest stars all the way out to the full size of our galaxy. Beyond the nearest stars and their wide emptiness lies the next rung of the ladder, which is the full size of the galaxy that holds us. The Milky Way is not simply a scattering of stars, but a single, enormous structure, a slowly turning wheel of suns bound together by gravity, and its size is the next great leap upward. To cross from one side of it to the other is a journey of a wholly different scale than the step to the nearest star. And yet the galaxy is still only one island among countless others. The Milky Way is a barred spiral, a flattened disk of stars wound into great curving arms, with a thickened glow of older stars at its center. From edge to edge, the disk spans about 100,000 light-years. That is the distance. Light itself, moving at its full speed, takes 100,000 years to cross. The same beam that crosses the planetary solar system in half a day needs 1,000 centuries to span the galaxy. The leap from the nearest star at 4 light-years to the whole galaxy at 100,000 is a climb of more than 20,000 times. The disk is wide but thin. Through most of its span, it is only a few thousand light-years thick, so that the galaxy is shaped less like a ball than like an enormous, slowly spinning plate. The Sun sits within this plate, far out toward the edge, about 26,000 light-years from the center, in a minor spiral feature between two of the larger arms. From this position, looking inward along the plane of the disk, the combined light of distant stars blends into the soft band that crosses the night sky and gives the galaxy its name. At the center of this great wheel lies a dense, rounded gathering of older stars, and hidden within it sits something extraordinary, a black hole of enormous mass around which the whole galaxy slowly turns. The stars near that center are packed far more closely than the ones out where the Sun drifts, crowding together in a brilliant region that the dust of the disk hides from direct view. From our position far out toward the rim, more than halfway to the edge, the center is only a soft glow behind intervening clouds, its true nature revealed by patient watching across kinds of light the eye cannot see. The galaxy is not uniform, but layered, dense, and bright at the middle. thinning gently outward to the faint scattered edge where our own star quietly belongs. Within this wheel turn an enormous number of stars. Estimates run from 100 billion to perhaps 400 billion suns, each one a star in its own right, many with worlds of their own. The nearest star, which took 6,000 years to reach even in imagination, is only one of these hundreds of billions, and all the others are farther. The galaxy is not a place that could be toured star by star in any span of time that means anything. It is a structure so large that light, the fastest thing there is, spends 1,000 centuries simply crossing it. And yet the whole of this immense wheel turns. The Sun and all its neighbors sweep slowly around the galactic center, carried along at a couple of 100 kilometers every second, and even at that speed, a single full circuit takes something like 225 to 250 million years. The Sun has made only about 20 such circuits in its entire existence. The galaxy does not rush. It turns with enormous patience, one slow revolution stretching across hundreds of millions of years, and the stars within it ride that turning like flecks of light, embedded in a wheel almost too large to comprehend. This is the island that holds everything we have ever known. Every star ever named, every world ever studied, every point of light the unaided eye has seen at night belongs to this one galaxy. And the galaxy, for all its hundreds of billions of stars and its 100,000 light-years of width, is a single member of a population that numbers in the hundreds of billions. To cross it is the work of 1,000 centuries at the speed of light. To cross what lies beyond it is the work of far longer, and it is to that next, greater scale that the ladder now turns. To cross the galaxy is to undertake a journey that dwarfs every interstellar step, and the numbers attached to it begin to leave the human scale behind entirely. The galaxy is 100,000 light-years across, and the meaning of that figure becomes clearer when it is set against the speeds we can actually reach. At every speed available to us, and even at the speed of light itself, crossing the galaxy is a project measured not in lifetimes, but in ages of the world. At the speed of light, the crossing takes 100,000 years. A beam of light leaving one edge of the galaxy arrives at the other only after a span longer than the whole history of our species in its present form. Nothing can travel faster than that beam, so 100,000 years is the shortest possible crossing time, the floor beneath which no journey across the galaxy can ever fall. Even an imaginary traveler moving at the ultimate speed the universe allows would spend 1,000 centuries simply going from one side of our own galaxy to the other. Our fastest machines, of course, move far slower than light. The swiftest object ever built reaches about 190 kilometers per second, which sounds enormous and is, by human standards, almost unimaginably fast. Yet light moves more than 1,500 times faster still. At that record machine speed, crossing the galaxy would take on the order of 160 million years. A probe, launched at the dawn of the age of the great reptiles, moving faster than anything we have ever made, would only now be completing a single crossing of the galaxy that holds us. It helps to remember how the stars are spread, because it explains why no shortcut exists. The galaxy is not crowded. Its hundreds of billions of stars are scattered through an enormous volume, with light-years of emptiness between them, the same thin darkness that surrounds the nearest star. A journey across the galaxy is not a series of short hops between close-set suns. It is a long passage through mostly empty space, with each star a distant island, and the next one always years or centuries of travel beyond. The emptiness that separates the nearest stars is the same emptiness, multiplied many thousands of times, that fills the breadth of the galaxy. There is a quiet way to feel the size of it. Picture the entire solar system, out to the edge of the sun's frozen outer shell, shrunk down to the size of a small coin. On that scale, the galaxy would still stretch across a distance comparable to the width of a continent. The coin-sized solar system, which takes our machines tens of thousands of years to cross, would be one tiny disk lost somewhere in a structure the size of a landmass. That is the leap the ladder has just made, from the coin to the continent. And the continent is still only one galaxy among hundreds of billions. And nothing about that continent is crowded. Spread across its breadth are a few 100 billion stars, but they are scattered so thinly that a traveler crossing the galaxy would pass years of empty darkness between one star and the next. The same near-perfect emptiness that surrounds the Sun, repeated across 100,000 light-years. The journey across the galaxy is not a passage through a field of suns, but through a great and patient darkness, with the stars set so far apart that the crossing is mostly night. Even moving at the speed of light, a traveler would spend 1,000 centuries in that darkness, the stars drifting past slow and far, the far side of the galaxy never seeming to come any closer. So the galaxy, crossed in 100,000 years by light and in 160 million by our fastest machine, stands as the largest single object the journey has yet reached. It is the outer limit of the familiar, the boundary of the one structure we belong to. Beyond its edge, the stars thin out and stop, and a new kind of emptiness begins, larger and quieter than the space between stars. It is the space between galaxies, and crossing it carries the ladder to a scale where even the galaxy becomes a single point of light among many. Beyond the edge of the Milky Way, the first things to be reached are not far-off strangers but close companions, the small galaxies that travel alongside our own. The Milky Way does not drift alone. It is accompanied by a retinue of smaller galaxies, dim and modest beside the great spiral, held near it by gravity and circling it across enormous spans of time. These companion galaxies are the first stepping stones out into intergalactic space, and reaching them is the next rung of the ladder. The best known of these companions are two softly glowing patches, visible from the southern skies of the Earth, two small galaxies that orbit the Milky Way. They lie roughly 160,000 to 200,000 light-years away, which is to say only a little farther than the width of the galaxy itself. They are small, irregular collections of stars, far less grand than the Milky Way, but they are true galaxies, and they mark the beginning of the space beyond our own. To reach them, a traveler would cross a gap larger than the whole breadth of our galaxy. These two are only the brightest of a larger family. The Milky Way is surrounded by dozens of small dwarf galaxies, faint gatherings of stars that circle it like a swarm of dim satellites. Most are so faint that they were only found with patient searching, each one a sparse cloud of stars bound to the Milky Way and moving slowly around it. Together with their larger sibling, they form a small local court of galaxies, all of them held within the gravity of the great spiral at their center, all of them traveling together through the larger dark. The distances to these companions, while enormous, are still small compared with what comes next. 160,000 light-years, the gap to the nearest bright companion, is barely more than the width of the Milky Way. At the speed of light, the crossing takes 160,000 years. At the speed of our fastest machine, it would take some 250 million years, longer than the Sun takes to circle the galaxy once. These nearby galaxies are companions in the loosest sense, neighbors separated by gulfs that no journey could close in any span of time that means anything to us. What these companions reveal is that galaxies, like stars, come in groups. Just as the Sun belongs to a loose neighborhood of nearby stars, the Milky Way belongs to a loose gathering of nearby galaxies, bound together and moving as one. The small companion galaxies are the inner members of that gathering, the closest of the Milky Way's galactic kin. They are the first sign that the ladder is entering a new realm, where the unit is no longer the star, but the galaxy, and where the distances are measured not in thousands of light years, but in millions. So the companions mark a threshold. Behind lies the Milky Way, the one island we belong to, crossed by light in 1,000 centuries. Ahead lie the other galaxies, beginning with these dim satellites and reaching outward to far grander structures. The nearest of the truly great galaxies, a spiral as large as our own or larger, still waits far beyond these small companions, across a gulf more than 10 times wider. It is the next major rung, and reaching it carries the journey across the first truly intergalactic distance, out to a galaxy whose light is older than humanity itself. Across the gulf beyond our small companions lies the nearest great galaxy, a spiral as large as our own, and reaching it is the first truly intergalactic step of the journey. This galaxy, called Andromeda, is the nearest major galaxy to the Milky Way, and on a clear, dark night, it can be seen with the unaided eye as a faint smudge of light. That faint smudge is the most distant thing most people will ever see without a telescope, and its light has been traveling toward the Earth for an almost unthinkable span of time. Andromeda lies about 2.5 million light-years away. The number marks a steep climb up the ladder, from the 160,000 light-years to the nearest companion galaxy, to 2.5 million to the nearest great one, a leap of more than 10 times. It means that the light now arriving from Andromeda, the light that forms that faint smudge in the night sky, left the galaxy about 2.5 million years ago. It began its journey long before our species existed in its present form. To look at Andromeda is to look at light older than humanity. Andromeda is not a lesser thing than the Milky Way. It is a great spiral galaxy, comparable in size to our own, or somewhat larger, holding hundreds of billions of stars of its own, with its own companion galaxies circling it, its own arms wound around its own bright center. Seen up close, it would fill the sky, a wheel of stars as grand as the one we belong to. From 2.5 million light-years away, it is reduced to a dim oval patch, easy to overlook, and yet it is an entire galaxy, a structure every bit as enormous as the Milky Way, simply seen across an enormous distance. Around Andromeda circle its own small companion galaxies, dim satellites bound to it just as our companions are bound to us, so that the slow approach of the two great spirals is also the approach of two whole families of galaxies. Seen through a telescope, Andromeda spreads far wider than the full moon across the sky, its faint outer arms reaching across a span the unaided eye cannot make out. Only its bright center shows to the naked eye, which is why it appears as a small smudge rather than the enormous wheel it truly is. The light gathering in that smudge has crossed 2.5 million years of emptiness to arrive, unchanged, at the back of a single eye on a dark night, a quiet messenger from a galaxy that set it loose before the first people walked the Earth. The two galaxies are not standing still relative to each other. Andromeda and the Milky Way are slowly drawing together, pulled by their mutual gravity, approaching at something over 100 kilometers every second. Across a span of several billion years, they will meet and gradually merge, passing through each other and settling, over a long stretch of time, into a single, larger galaxy. The stars within them are so widely separated that almost none will collide. The two great clouds of suns will simply drift through one another and slowly combine. It is a meeting measured in billions of years, gentle and unhurried despite its scale. Reaching Andromeda, even in imagination, stretches the numbers further than anything before. At the speed of light, the crossing takes 2.5 million years. At the speed of our fastest machine, the journey would take something on the order of 4 billion years, a span comparable to the entire age of the Earth. A probe launched today at that record speed, aimed at Andromeda, would arrive only after the Sun itself had swelled and died, and the Earth had long ceased to exist. The machine would outlive its maker's star, and very nearly its maker's galaxy, and still, it would only just be arriving at the nearest great galaxy of all. And Andromeda, for all its distance, is a close neighbor. It is the nearest of the large galaxies, the first major stop beyond the Milky Way, part of the same small bound gathering that our galaxy belongs to. Everything beyond it is farther, by amounts that make even 2.5 million light-years seem modest. The ladder has now reached the scale of galaxies and the millions of light-years between them, and the next rungs carry it outward, past the local gathering entirely, into the realm of clusters, where galaxies are counted not in dozens, but in thousands. The Milky Way and Andromeda are not solitary giants, but members of a small bound family of galaxies, and that family is the next structure on the ladder. It is called the local group, and it is the gathering of galaxies held together by their own shared gravity, moving as one through the larger cosmos. Understanding the local group matters more than its size alone would suggest, because it is the one structure that will stay with us no matter how the rest of the universe behaves. Everything in it is bound. Everything beyond it is not. The local group contains two great spiral galaxies, the Milky Way and Andromeda, along with a third and smaller spiral and several dozen dwarf galaxies scattered around and between them. The third spiral, called Triangulum, lies a little farther than Andromeda, around 2.5 to 3 million light-years away, and is the third largest member of the group. Around these three larger galaxies circle the many dwarfs, the small companion galaxies, all of them bound into a single, slowly moving assembly of perhaps 80 or more galaxies in total. The whole local group spans roughly 10 million light-years across. That is the next rung above the distance to Andromeda, a structure 4 times wider than the gap to our nearest great neighbor. Within that span, the member galaxies drift and orbit one another, drawn together by gravity, some falling slowly inward, the two largest destined eventually to merge. It is a quiet, bound community of galaxies, moving through the surrounding emptiness as a single gravitational unit, holding itself together across the ages. What makes the local group special is precisely that it holds together. The galaxies within it are bound tightly enough by gravity that the expansion of the universe cannot pull them apart. Across the enormous spans of future time, while the rest of the cosmos draws steadily farther away, the members of the local group will remain, eventually merging into a single great galaxy. This bound island is the one part of the universe beyond our own galaxy that will always, in principle, stay within reach. It is the only galactic neighborhood that does not recede. That fact will matter greatly when the second wall comes into view, but even now it carries a quiet weight. Of all the hundreds of billions of galaxies in the observable universe, only the few dozen in our own bound group are truly ours to keep. They are near enough and bound tightly enough that the growing space between galaxies will never carry them away. Everything else, every other galaxy, every cluster and supercluster lies on the far side of a slow and widening gulf that gravity within the local group is strong enough to resist, but that nothing outside it can. So the local group is the island that stays, a bound gathering of galaxies 10 million light-years across, drifting together through a universe that is otherwise slowly coming apart. It is the largest structure the ladder has reached that will remain forever within reach. Beyond its edge, the galaxies are no longer bound to us, and the second wall begins to make itself felt. But that lies ahead. For now, the ladder simply notes the size of the island, 10 million light-years of bound galaxies, and turns toward the far larger and unbound structures that lie beyond it, where galaxies gather not in dozens, but in thousands. Beyond the bound island of the local group, the galaxies gather into far larger assemblies, and the ladder climbs into the realm of clusters. Where the local group holds a few dozen galaxies, a great cluster can hold hundreds or thousands, all drawn together into a single enormous swarm. These clusters are among the largest structures in the universe, held together by their own gravity, and reaching even the nearest of them carries the journey across tens of millions of light-years of intergalactic space. The nearest large cluster of galaxies lies in the direction of a particular constellation and is known as the Virgo cluster. It sits roughly 50 to 65 million light-years away, and it contains well over 1,000 galaxies, many of them great spirals and giant ellipticals, far larger than the Milky Way. At its center lies an enormous elliptical galaxy, one of the most massive in the nearby universe, surrounded by a swarm of lesser galaxies, all bound together in a single gravitational gathering, many millions of light-years across. Our own local group lies near the outer fringes of the influence of this great cluster, and is in fact slowly falling toward it, drawn by the enormous gravity of all those gathered galaxies. The local group is, in a sense, a distant suburb on the edge of a far grander city of galaxies. We are not part of the Virgo cluster itself, but we feel its pull, and across enormous spans of time the whole local group drifts slowly in its direction, one small bound island sliding toward a far larger gathering of light. The distances here have climbed again. To cross from the local group to the Virgo cluster is to traverse some 50 million light-years, 5 times the width of the local group itself. At the speed of light, that crossing takes 50 million years and more. The number has now left every human and even every planetary timescale behind. 50 million years ago, the Earth was a different world entirely, and a beam of light setting out then from the Virgo cluster would only now be arriving. Each rung of the ladder now spans a length of time longer than whole chapters of a planet's history. Clusters like Virgo are the largest things in the universe that gravity still holds firmly together. Within them, galaxies orbit one another, swarming through a common haze of hot gas, bound into a single structure for the long term. They mark a kind of upper limit to what gravity can gather and keep. Above the scale of clusters, the structures grow larger still, but they are no longer fully bound. They are looser associations, held in shape more by the pattern of the cosmos than by gravity alone. The cluster is the largest firmly bound island, and Virgo is the nearest great one. So the ladder has reached the realm of clusters, where galaxies are counted in thousands and distances in tens of millions of light-years. The nearest such cluster lies 50 to 65 million light-years off, and our own small group drifts slowly toward it through the surrounding dark. Beyond the clusters lies something larger and looser still, a structure that gathers clusters themselves into enormous flowing assemblies, hundreds of millions of light-years across. It is to that scale, the scale of superclusters, that the journey now climbs, where even great clusters become single points in a far wider pattern. Above the scale of clusters, the ladder reaches the superclusters, the enormous assemblies where clusters themselves gather into far larger patterns. A supercluster is not a tight-bound swarm like a single cluster, but a sprawling association of many clusters and groups linked together across hundreds of millions of light-years. At this scale, the individual galaxy has become almost invisibly small, and even great clusters of 1,000 galaxies are reduced to single knots in a structure of almost unimaginable extent. Our own local group and the Virgo cluster it drifts toward both belong to a still larger structure, a supercluster that has been mapped by following the slow flows of galaxies through space. This great structure has been given a name meaning immense heaven, and it spans something like 520 million light-years from end to end. Within it, many thousands of galaxies and many separate clusters are caught up in a shared, slow drift, all of them flowing gently toward a common region of especially strong gravity deep within the supercluster. That region of strong gravity is sometimes called the Great Attractor, a concentration of mass toward which our whole local portion of the universe slowly drifts. It cannot be seen clearly, partly because it lies beyond the crowded band of our own galaxy, but its pull can be measured in the motion of thousands of galaxies, all of them sliding in the same general direction across the supercluster. The Milky Way, the local group, the Virgo cluster, and countless other galaxies are all part of this enormous, patient flow, carried along together through space toward the same far-off gathering of mass. The scale of a supercluster is difficult to hold, even in outline. 500 million light-years is more than 50 times the width of the local group and 10 times the distance to the Virgo cluster. To cross such a structure at the speed of light would take more than 500 million years, a span longer than the time since complex life first spread across the Earth's oceans. And a supercluster, enormous as it is still not the whole pattern. It is one feature among many in a structure larger still, the largest pattern there is, into which all the superclusters together are woven. It is worth noticing that these greatest structures are no longer fully bound by gravity. A single cluster holds itself together and will endure, but a supercluster is a looser thing, a pattern in the distribution of galaxies rather than a tightly bound object. As the universe expands, the great flows within superclusters are slowly being overcome by the growing space between galaxies. The superclusters are, in a sense, the last large patterns the universe will hold before expansion smooths the grandest flows away. They are enormous, and they are also, on the longest timescales, temporary. So the ladder has climbed to the scale of superclusters, structures hundreds of millions of light-years across, within which whole clusters drift as single points, caught in slow cosmic flows. Our galaxy belongs to one such supercluster, sliding with thousands of others toward a distant gathering of mass. Above this scale lies only one thing larger, the full pattern into which all superclusters are arranged, the largest structure known. It is the texture of the universe itself at the grandest scale, a web of light and emptiness, and it is the final rung before the horizon. At the largest scale of all, the universe reveals a single grand pattern, and it is the last structure the ladder reaches before the horizon. Seen broadly enough, the galaxies are not scattered evenly through space. They are arranged along enormous threads and sheets, gathered into a structure that resembles a web or a foam, with the galaxies strung along its strands, and almost nothing at all in the great spaces between. This pattern, the cosmic web, is the texture of the universe at its grandest scale, and within it every cluster and supercluster is only a brighter knot along a thread. The strands of this web are long filaments of galaxies, stretching for hundreds of millions of light-years, where galaxies and clusters gather most thickly. Where several filaments cross, the galaxies gather densest of all, forming the great clusters and superclusters. Between the filaments lie the voids, enormous near-empty bubbles, tens or even hundreds of millions of light-years across, where almost no galaxies are found at all. The universe at this scale looks like a sponge or a mass of soap bubbles, with the galaxies clinging to the walls and edges and the interiors standing all but empty, The voids are the largest empty spaces in existence. A single void can span 100 million light-years or more of almost perfect emptiness, holding only a stray galaxy or two within a volume that could contain thousands. If the bright filaments are where the light gathers, the voids are where the universe is mostly nothing at all, immense rounded hollows of darkness that take up most of the volume of the cosmos. Most of space, at the largest scale, is void. The bright web of galaxies is the thin tracery around the edges of an enormous dark foam. This web is the largest pattern there is. There is no structure above it, no still grander gathering into which the cosmic web itself is arranged. It is the end of the hierarchy that began with moons around planets and climbed through stars, galaxies, clusters, and superclusters. Beyond the scale of the web, there are no larger structures, only more of the same web, repeating outward in every direction with much the same texture, until it reaches the limit of what can be seen. The cosmic web is the universe wearing its final and largest shape. To cross even a single great strand of this web is the work of hundreds of millions of years at the speed of light, and to cross the whole web, out to the limit of sight, is the figure the entire journey has been climbing toward. The web fills the observable universe from edge to edge, its filaments and voids repeating outward to the horizon of sight, some 46.5 billion light-years away. The ladder, which began with a single light second to the moon, has reached the structure that fills all of visible space, the grandest and final rung before the edge. And here, at the scale of the web, the second wall finally comes fully into view. These greatest strands and voids are not held together by gravity. They are being slowly carried apart by the expansion of space itself, the filaments stretching, the voids widening, the galaxies along the strands drifting ever farther from one another across the ages. The web is not a fixed scaffold, but a slowly growing one, expanding everywhere at once. To understand how long it would take to cross it, and why most of it can never be crossed at all, the journey must now turn from the size of the universe to the strangest fact about it, which is that the universe is growing. The ladder has one final rung, and it is not a structure, but a boundary, the edge of everything that can be seen. This boundary is the horizon of the observable universe, the farthest distance from which light has had time to reach us since the universe began. It is the outer limit of the cosmic web, the place where the journey outward finally runs out of universe to see, and it lies some 46.5 billion light-years away in every direction. It is the top of the ladder, and it is unlike every rung below it. Unlike the planets or the stars or the galaxies, this horizon is not an object. There is nothing there to arrive at, no wall, no edge of space, no boundary marker hanging in the dark. The horizon is simply the distance beyond which the light of more distant things has not yet had time to reach us. Past it, there is surely more universe, more galaxies, more cosmic web, but their light is still on its way and has not yet arrived, and so they remain unseen. The horizon is a limit of time and sight, not a limit of space. Because it is a horizon of sight, it is also a horizon of age. The most distant light that reaches us is the oldest light there is, having traveled for almost the entire age of the universe. To look out toward the horizon is to look back toward the beginning, to see the universe not as it is now, but as it was when it was young. At the very edge lies the faint afterglow left over from the universe's hot early days, a soft glow of ancient light coming from every direction, the oldest thing any eye or instrument can detect. The horizon of distance is also the horizon of the past. That faint afterglow at the edge of sight is the oldest light in existence, released when the young universe first cooled enough to become clear, and it has been traveling toward us ever since, across nearly the whole age of the cosmos. It comes from every direction at once, a soft and even glow far too faint and too stretched for the eye to register, detectable only by instruments built to listen for it. To map it is to see the universe as it was in its earliest clear moment, long before the first stars, long before any galaxy had formed. Beyond that glow, there is no seeing further, not because space ends there, but because earlier than that, the universe was not yet clear, and no light from before it can reach us. The afterglow is the wall of sight itself. The size of the observable universe, measured out to this horizon, is about 93 billion light-years across. That figure has waited at the top of the ladder since the journey began, and now it stands fully revealed, with every rung below it climbed in turn. From the single light second to the moon, through the light-years to the nearest stars, the 100,000 light-years of the galaxy, the millions to Andromeda, the tens and hundreds of millions through clusters and superclusters, the ladder has climbed at last to the tens of billions of light-years that span all of visible space. Each rung was enormously larger than the last, and the climb has been steep beyond imagining. It is worth holding, for a quiet moment, the full shape of what has been built. The observable universe is a sphere of old light, 93 billion light-years from side to side, filled with the cosmic web of galaxies, centered on the observer with the oldest light of all, glowing faintly at its edge. This is the thing the journey set out to cross. It is the largest measurable distance there is, the full extent of everything that can be seen, and the question of how long it would take to cross it can now, at last, be answered honestly. But the answer requires facing the two walls directly, and the ladder has carried us to the place where they can no longer be postponed. The first wall is the speed of light, which makes even the smaller rungs take ages to cross. The second wall is the expansion of space, which makes most of this enormous sphere impossible to cross at all. Having climbed the whole ladder and seen the full size of the observable universe, the journey now turns to measure it, first against our fastest machines, then against light itself, and finally against the growing of space that changes everything. Having built the whole ladder of distance, the journey now measures it against reality, beginning with the fastest objects human hands have ever made. It is one thing to speak of light years and crossing times in the abstract, and another to set those distances beside the actual speed of the machines we can build. The contrast is humbling, and it is also clarifying, because it shows exactly where we stand on the ladder we have climbed. The truth is that our fastest machines are extraordinarily fast by human standards, and almost motionless against the cosmos. The outbound probes that have traveled farthest from the Earth move at roughly 17 kilometers every second relative to the Sun. That is fast enough to cross the distance from one city to another in the time it takes to draw a breath, fast enough to leave any aircraft or rocket on Earth far behind. These machines have been flying for more than 4 decades, and they are the most distant objects our species has ever sent, now drifting in the space beyond the Sun's bubble of wind. 17 kilometers per second is the speed of our longest journeys. Faster still is a small probe built to skim close to the Sun, dipping again and again into the Sun's outer atmosphere and using the Sun's enormous gravity to gather speed. At its closest passes, it has reached about 190 kilometers every second, which is roughly 430,000 miles per hour. That is the fastest any object built by human hands has ever traveled. Nothing we have made has ever moved more quickly than this small craft at the bottom of its dive toward the Sun. It is the current record for the speed of anything human. And yet, set against light, even this record speed is almost nothing. Light moves more than 1,500 times faster than that fastest probe. Where light crosses 300,000 kilometers in a second, the probe crosses 190. To put it another way, the fastest thing we have ever built travels at a little more than 1 part in 2,000 of the speed of light. The gap between our best speed and light speed is not small. It is a gulf of more than 1,000-fold, and it does not close. These speeds, the record-setting and the merely very fast, are the true measure of what human travel can presently achieve. They are the speeds that would carry any real traveler, any real machine, across the distances of the ladder. The crude craft that have carried people have been slower still, reaching the moon in a few days, but never approaching the speed of the fastest uncrewed probes. When we ask honestly how long it would take to cross the universe, these are the numbers that must be used, the real speeds of real machines, not the speed of light that no object with mass can reach. So the machines are set against the ladder, and the result is the quiet payoff of the journey so far. At a little under 200 kilometers per second, our fastest probe is the swiftest thing we have ever made, and it would still take ages beyond counting to cross even the nearer rungs of the ladder. The numbers that follow are not meant to discourage. They are meant to give a true sense of scale, to show with honest figures just how enormous the distances are. And so the next step is simply to ask, plainly, how long our fastest machine would take to climb each rung of the ladder we have built. Setting the fastest machine against each rung of the ladder gives the first honest answer to the question, and the numbers climb as steeply as the ladder itself. The fastest object ever built moves at about 190 kilometers per second, and at that speed, each step outward takes a span of time longer than the one before. Gathered together, these crossing times trace the whole shape of the journey, from the nearest star to the edge of the visible universe, in a single slow ascent of numbers. To the nearest star, at 4¼ light-years, the fastest machine would take about 6,600 years. 6,000 years is longer than all of recorded history, longer than the span from the first written words to the present day. A probe launched toward the nearest star, at record speed, would arrive only after a stretch of time longer than civilization itself has so far lasted. And the nearest star is the smallest interstellar step there is, the gentlest possible version of the journey. To cross our own galaxy, 100,000 light-years from side to side, the same machine would take about 160 million years. A probe launched when the great reptiles still walked the Earth, moving at the fastest speed we have ever achieved, would only now be completing a single crossing of the galaxy. To reach the nearest great galaxy, Andromeda, at 2.5 million light-years, the journey would stretch to about 4 billion years, a span comparable to the entire age of the Earth, longer than the time life has existed on this world. And to cross the whole observable universe, 93 billion light-years from edge to edge, the fastest machine we have ever built would take something on the order of 100 trillion years. That number has left every comparison behind. It is many thousands of times longer than the current age of the universe. It is longer than the age of the universe, multiplied by itself many times over. A machine launched at the first moment of time, at our best speed, would have crossed only the smallest fraction of the universe by now, and would go on traveling for an almost endless span before reaching the far side, if it ever could. These figures share a single, quiet lesson. At the speeds we can actually reach, the universe is not crossable in any span of time that means anything. The nearest star alone outlasts all of history. The galaxy outlasts the age of complex life. The nearest great galaxy outlasts the Earth. And the universe as a whole outlasts every comparison the mind can offer. The machine, our fastest creation, would outlive its makers, their star, their galaxy, and very nearly the age of the cosmos itself, and still it would only be beginning. There is a strange dignity in that image, the patient machine crossing the dark, long after everything that built it is gone. But it also points toward an obvious question. If our fastest machines are so far too slow, could we not simply build something faster? Could a great enough effort lift a traveler close to the speed of light, and so shrink these enormous times towards something bearable? The answer is no, and the reason why is the first of the two walls, the wall that stands in the way of ever reaching the speed of light at all. To that wall, the journey now turns. The natural hope, faced with such enormous crossing times, is simply to go faster. And it is worth explaining gently why that hope runs into a wall. If our fastest machine is far too slow, perhaps a greater one could approach the speed of light and shrink the journey to something reasonable. The trouble is that approaching the speed of light is not a matter of building a stronger engine. It runs into the deep structure of motion itself, and the closer one tries to come to light's speed, the harder the universe pushes back. Part of the difficulty is a simple matter of fuel. A rocket carries its fuel with it, and that fuel has weight, and lifting that weight requires still more fuel, which adds still more weight. To go faster, a craft must carry more fuel, but the extra fuel makes the craft heavier, which demands more fuel again. The numbers climb steeply, so that even reaching a modest fraction of the speed of light by ordinary means would require a quantity of fuel beyond anything imaginable, far more than the craft itself, stacked up in a tower of fuel carrying fuel that quickly becomes absurd. Even setting fuel aside, there is a more fundamental barrier written into the nature of speed. The faster an object moves, the more energy it takes to speed it up further. And as the speed approaches that of light, the energy required does not merely grow, but climbs without limit. To reach the speed of light exactly would take an infinite amount of energy, which is another way of saying it cannot be done at all. The speed of light is not a target that a powerful enough engine could hit. It is a ceiling that nothing carrying mass can ever touch. The energies involved, even to approach light's speed, are difficult to overstate. To accelerate a single substantial craft to a large fraction of the speed of light would demand an amount of energy comparable to the entire output of a civilization across a long span of time. And then, to stop again at the far end, the whole enormous cost would have to be paid a second time, because slowing down from such a speed takes just as much energy as speeding up. The faster one wishes to go, the more steeply these costs rise, until they pass beyond anything a civilization could ever gather. So the speed of our machines is not a problem that effort alone can solve. There is a true ceiling, set by the nature of energy and motion, that keeps any real traveler far below the speed of light. We will not be crossing the galaxy, let alone the universe, at anything close to light's speed. The fastest we can realistically imagine moving is some modest fraction of it, and even that lies far beyond our present reach, demanding energies we cannot supply and patience no civilization has yet shown. And yet, to be as generous as possible to the dream of crossing the universe, it is worth granting the impossible for a moment. Suppose the wall of energy could somehow be climbed, and a traveler could move at the very speed of light itself, the fastest the universe allows anything to go. Suppose the journey could be made at light's own pace. Even then, as the next step will show, the crossing times remain enormous, and the deepest figure of all, the time for light itself to cross the universe, turns out to be longer than the universe has existed. The floor beneath all crossing times is light's speed, and even that floor lies impossibly far below the distances we have climbed. Granting the impossible, then, the journey now imagines traveling at the speed of light itself, and finds that even this changes less than one might hope. The speed of light is the flaw beneath all crossing times, the shortest any journey across a given distance can possibly take. Nothing can cross a light year in less than a year, by definition, and nothing can cross the universe faster than light can. So to ask how long light itself takes to cross each rung of the ladder is to ask for the best possible case, the fastest any crossing could ever be. At the speed of light, crossing our own galaxy takes 100,000 years. That is the flaw for the galaxy, the shortest possible crossing, and it is already longer than the whole history of our species in its present form. To reach the nearest great galaxy, Andromeda, light takes 2.5 million years, and so 2.5 million years is the fastest any journey there could ever be made. To cross the bound island of the local group takes about 10 million years at light speed. Even at the ultimate speed, the nearer galaxies lie millions of years apart. Climbing further, the floor rises with the ladder. To reach the nearest great cluster of galaxies takes light 50 to 65 million years. To cross a supercluster takes more than 500 million years, even for light. Each of these is the shortest possible crossing, the time for the fastest thing in the universe to make the journey, and each is longer than immense chapters of a planet's history. At light's own speed, the realm of clusters and superclusters is still hundreds of millions of years wide, and no traveler of any kind could ever cross it more quickly. And then comes the figure the whole journey has been climbing toward. To cross the full breadth of the observable universe, 93 billion light-years from edge to edge, light itself would take about 93 billion years. That number is the flaw beneath all crossing times for the universe as a whole, the fastest the crossing could ever conceivably be made. And it is far longer than the universe has so far existed. The universe is about 13.8 billion years old. 93 billion years is nearly 7 times that age. The meaning of this is worth holding gently, because it is one of the strangest facts in all of astronomy. Even light, the fastest thing there is, could not have crossed the present-day observable universe in the whole time the universe has existed. A beam of light that set out at the very first moment of time, at the beginning of everything, traveling at full speed ever since, would have crossed only a fraction of the current breadth of the observable universe by now. The universe is wider, measured across right now, than the distance light could have traveled since the universe began. Nothing has had time to cross it. Nothing could. This is the first wall seen in full. The speed of light is the flaw, and even that flaw lies impossibly far below the size of the cosmos. At our best real speeds, the universe takes 100 trillion years to cross. At the speed of light, it still takes 93 billion. But even this is not the whole of it, because every figure so far has quietly assumed that the distances stay fixed while the journey is made. They do not. The universe is growing, the far galaxies drifting steadily farther, even as any traveler approaches. And once that growth is taken into account, the picture shifts from merely enormous to something stranger still. It is to the second wall, the expansion of space, that the journey now finally turns. The deepest reason the universe cannot be crossed is not about speed at all, but about the nature of space, and it is the gentlest and strangest idea in the whole journey. Until now, every crossing time has quietly assumed that the distances stay fixed, that a galaxy 2.5 million light-years away will still be 2.5 million light-years away when a traveler arrives. This assumption is false. The space between distant galaxies is growing, steadily and everywhere, and that growth changes the question of crossing the universe from a matter of patience to a matter of possibility. Space is not a fixed stage across which galaxies move like actors on a floor. The stage itself stretches. Between any two distant galaxies that are not bound together by gravity, new space is continually appearing, so that the distance between them grows with time, even though neither is traveling through space toward or away from the other. The galaxies are not flying apart through space. The space between them is swelling, carrying them farther from one another as it grows. This is the expansion of the universe, and it happens everywhere at once. A familiar picture helps, so long as it is held loosely. Imagine a loaf of bread studded with raisins as it bakes and rises. Each raisin stays the same size, but the dough between them swells, and so every raisin moves farther from every other raisin, not by crawling through the dough, but by being carried along as the dough expands. From the point of view of any one raisin, all the others appear to move away, and the farther ones appear to move away fastest. The galaxies are the raisins, and the swelling dough is space itself. This swelling of space is not something happening inside the universe, the way a tide rises within a sea. It is the universe itself growing larger everywhere, the distances between all unbound things lengthening together in the same quiet way. It has been going on since the beginning, and the light from distant galaxies carries the proof of it, stretched toward redder colors by the growing of the space it crossed on its way to us. The farther the galaxy, the more its light has been stretched, because the more space lay between to do the stretching. Every distant galaxy we observe is shifted toward red in just this way, a steady reddening that grows with distance, the visible mark of a universe that has been expanding the entire time its light was in flight. This expansion does not pull apart the things that are bound tightly together. An atom holds itself together by its own forces and does not grow. A star, a planet, a single galaxy, even a bound group of galaxies like our own local group, are all held together by gravity strongly enough to resist the swelling of space. Within these bound islands, distances stay fixed. It is only across the great gulfs between separate galaxy groups, where gravity is too weak to hold, that the expansion makes itself felt. The bound stays bound. The unbound drifts apart. The expansion is also without a center. There is no point from which everything is flying outward, no place that could be called the middle of the swelling. From every galaxy the view is the same. All the distant galaxies appear to be receding, and the farther ones recede faster. An observer in Andromeda would see the Milky Way drifting away from them exactly as we see Andromeda's more distant neighbors drifting away from us. The expansion happens everywhere, uniformly, with no center and no edge. Every observer sits, apparently, at the still middle of a universe that is gently coming apart around them. This is the second wall, and it is unlike the first. The speed of light is a limit on how fast a traveler can move through space. The expansion of space is something else entirely, a growing of the distances themselves that no speed can overcome, because it does not race the traveler through space, but stretches the very ground the traveler must cross. To see how decisively this changes the journey, the next step is to follow the expansion outward, to the distance where the growth of space becomes so rapid that not even light can keep up with it. Following the expansion outward leads to one of the most surprising facts in all of cosmology, that beyond a certain distance, galaxies recede faster than light. The expansion grows with distance. The farther away a galaxy lies, the more space there is between us and it, and so the more new space appears between us each moment, and the faster the galaxy is carried away. Double the distance, and the rate of separation doubles. Triple it, and the rate triples. The recession is gentle nearby and grows steadily with every step outward. At small distances, the effect is almost too slight to notice. The nearby galaxies drift away slowly, their recession a soft addition to their other motions. But as the distance climbs into the billions of light-years, the rate of separation climbs with it, until at a certain critical distance, the space between us and a galaxy is growing so fast that the galaxy recedes at the speed of light itself. That critical distance lies around 14 billion light-years. A galaxy that far away is being carried from us as fast as light travels, purely by the swelling of the space between. Beyond that distance, the recession is faster than light. Galaxies more than about 14 billion light-years away, measured properly at this moment, are receding from us faster than light moves, not because they are speeding through space, but because the enormous span of space between us and them is growing so quickly. There is more space being added each second across that great gulf than light could ever cross in the same time. The far galaxies are swept away faster than any beam could chase them. It is important to hold, gently, why this breaks no law. Nothing is moving through space faster than light. No galaxy, seen by an observer right beside it, is racing past at superluminal speed. Every galaxy sits more or less still in its own patch of space, drifting only slowly through it. The faster-than-light recession is not motion through space at all. It is the stretching of space itself, the growth of the distance between, and that growth is not bound by the speed limit that governs motion. The speed of light limits how fast things move through space, not how fast space can grow. The consequence for any journey is decisive. Imagine a beam of light sent out toward a distant galaxy. The light moves through the space around it at its usual speed, gaining ground steadily. But if the total distance to the target is growing fast enough, new space is being added between the light and the galaxy faster than the light can cross it. The light makes progress locally and still falls behind overall, like a swimmer striking out strongly across a river whose far bank is drifting away faster than the swimmer can advance. For targets far enough away, the light never arrives at all. This is the heart of why most of the universe cannot be crossed. It is not merely that the distances are enormous, though they are. It is that the distances to the farthest galaxies are growing faster than light can close them, so that no signal and no traveler, moving at any possible speed, could ever reach them. The far galaxies are not simply a long way off. They are being carried away faster than light, beyond the reach of anything we could ever send. And this leads directly to the idea of a true edge of reachability, a horizon not of sight, but of contact, beyond which the universe is closed to us forever. The growing of space gives rise to a true boundary, a horizon beyond which nothing we send can ever arrive, and it is a different and stranger edge than the limit of sight. So far, the journey has spoken of the observable universe, the sphere from which light has had time to reach us. But there is a second and smaller horizon hidden inside it, a limit not on what we can see, but on what we could ever reach, even with a signal traveling at the speed of light, even given endless time. This is the cosmic event horizon, and it marks the true edge of the reachable universe. The reason this horizon exists is that the expansion of the universe is not merely continuing, but speeding up. A property of space itself, often called dark energy, is causing the expansion to accelerate, so that the great gulfs between galaxies grow not at a steady rate, but at an ever-increasing one. Because the expansion accelerates, there is a distance beyond which a beam of light sent out today will never arrive, no matter how long it travels, because the space ahead of it keeps growing faster and faster, forever staying ahead of the light. That distance is the cosmic event horizon. This horizon lies at a distance of roughly 16 to 18 billion light-years. A signal, or a traveler, sent out today could, in principle, eventually reach a galaxy that currently lies within that horizon, though the journey might take an enormous span of time. But a galaxy currently beyond that horizon is forever beyond reach. No message sent now will ever arrive there. No traveler leaving today, at any speed up to and including the speed of light, will ever cross the growing gulf to reach it. The galaxies beyond the event horizon are sealed away from us completely, not by distance alone, but by the accelerating growth of space. It is worth being careful about the two horizons, because they are easily confused. The observable universe reaches out to about 46.5 billion light-years. That is how far we can see, because light from that distance has had time to arrive. But the cosmic event horizon, the limit of what we could ever reach or signal, lies much closer, at 16 to 18 billion light-years. So there is an enormous shell of the universe between the event horizon and the edge of the observable universe that we can see but can never touch. We watch the light of those galaxies, ancient and red, while they themselves lie forever beyond any possible journey. It can help to picture the two horizons as two circles drawn around the same still center. The outer circle, far away, is everything we can see, the light that has reached us across the whole age of the universe. The inner circle, much closer, is everything we could ever touch, the limit past which the growing of space forever outruns any signal we might send. Between the two circles lies an enormous region of galaxies that are bright and clear in our instruments, and wholly beyond our reach, the visible relics of places we are completely cut off from. We live at the center of both circles at once, able to see far more of the universe than we will ever be able to reach. This is perhaps the most sobering single fact in the whole of the journey, and it is worth stating plainly and gently. We can see far more of the universe than we could ever reach. The light of distant galaxies pours in from regions we are utterly cut off from, regions that no ship and no signal could ever attain, because the space between has been growing too fast for too long and will only grow faster. To look out at most of the galaxies in the sky is to look at places that are visible and unreachable at once, present to the eye and closed to every journey. And so the question that began the night, how long would it take to cross the universe, finds its truest answer here. For most of the universe, the answer is not a number of years, however enormous. The answer is that it cannot be crossed at all, not slowly, not quickly, not even at the speed of light, not in any span of time, however long. The far galaxies are not merely distant. They are sealed away by the growing of space, on the far side of a horizon that no journey can pass. How much of the universe lies beyond that horizon, and how little remains within it, is the quiet and startling matter the next step takes up. When the reachable part of the universe is measured against the whole, the result is humbling, and it gives the final shape to the answer. The cosmic event horizon, lying at 16 to 18 billion light-years, encloses everything we could ever reach. The observable universe, reaching out to 46.5 billion light-years, encloses everything we can see. The space between those two horizons is enormous, and it is filled with galaxies that are visible and forever unreachable. The question is how the universe divides between the two, and the answer is stark. Of all the galaxies we can presently see, only a small minority lie within reach. By careful estimate, something like 94% of the galaxies in the observable universe are already permanently beyond any possible journey. More than 9 in every 10 galaxies whose light reaches our telescopes are galaxies we could never travel to, never signal, never affect in any way, Even if we set out this moment at the speed of light and traveled for the rest of time, we see them and they are closed to us. The overwhelming majority of the visible universe is unreachable. This majority is not unreachable because it is too far to bother with, the way a distant country might be too far to visit in a single life. It is unreachable in the strict and final sense that no journey by anything at any speed could ever arrive. The growing of space has placed these galaxies permanently beyond the event horizon, and they will only drift farther. They are as visible as the nearer galaxies and as utterly closed as if they lay in another universe entirely. We are surrounded by a great population of galaxies we can study in detail and never touch. There is something almost tender in the slowness of it, for no galaxy vanishes in an instant. Each one fades by degrees, its light stretching toward longer and redder wavelengths, growing dimmer and slower as it nears the horizon, until at last it thins past the point where any instrument could find it. The galaxies do not so much disappear as gradually quieten, sliding by gentle stages out of the reachable universe and into the unreachable one. From inside our own bound island, the change is far too slow to witness across any life or across the whole span of any civilization, unfolding instead across reaches of time longer than the present age of the universe. And the reachable portion is shrinking. As the expansion accelerates, more and more galaxies are being carried across the event horizon, slipping from the reachable region into the unreachable one by one, across the ages. A galaxy that lies just within reach today may, in the long future, find itself just beyond it, as the growing gulf carries it over the edge. The light of such galaxies stretches and reddens and dims as they recede, fading slowly toward invisibility. Over enormous spans of time, the universe we could ever reach grows steadily smaller, not larger. What remains, what stays reachable no matter how long the future runs, is only our own bound island, the local group. The few dozen galaxies held to us by gravity will stay with us, eventually merging into a single great galaxy, while everything beyond drifts forever away. In the far future, an observer in that merged galaxy, looking out, would see the rest of the cosmos to have receded beyond the horizon and faded from view, leaving only their own galaxy alone in an apparently empty dark. The reachable universe ends, in the end, at the edge of our own small bound group of galaxies. There is a way to hold this that is not bleak, and the journey will come to it before the night is over. For now, it is enough to have the honest shape of the answer. The universe cannot be crossed, not because we are too slow, though we are, but because most of it is sealed away by the growing of space, and the part that remains open is only our own small neighborhood of bound galaxies. The far reaches are visible and closed, present and unreachable, drifting quietly farther with every passing age. And yet there is one more idea, one last apparent loophole that must be looked at honestly before the journey can rest, and it concerns the strange behavior of time for a traveler moving near the speed of light. There is one apparent loophole in all of this, and honesty requires looking at it carefully before letting it gently close. So far, the journey has measured crossing times by the clocks of those who stay behind, and by those clocks, the numbers are enormous. But for a traveler moving very close to the speed of light, time itself behaves strangely. The faster one travels, the more slowly one's own clock runs compared with the universe outside, so that an enormous journey, measured by the universe, can feel surprisingly short to the traveler who makes it. This is not a trick or an illusion, but a genuine feature of the way motion and time are woven together. A traveler moving near the speed of light experiences time passing normally for themselves, but the universe around them ages far faster than they do. A journey that the outside universe measures in thousands or millions of years might be experienced by the traveler as only years or decades of their own felt time. In principle, the felt length of a journey can be shrunk enormously by traveling fast enough, even as the journey's length measured from outside stays as large as ever. If a traveler could keep up a steady, comfortable acceleration, the kind that would feel like ordinary weight underfoot, speeding up for the first half of the trip and slowing for the second, the effect becomes remarkable. By their own clock, such a traveler could in principle cross to the nearest great galaxy in a few decades of felt time and traverse far greater reaches of the universe within a single long lifetime as they experience it. The distance covered grows enormously, while the traveler's own felt time grows only slowly. By the traveler's clock alone, the universe begins to seem almost crossable. But the loophole closes on 3 separate counts, and each one is decisive. The first is the wall already met, the wall of energy. To hold that comfortable acceleration for years on end would require an amount of energy so far beyond anything imaginable that it is no more achievable than reaching the speed of light directly. The traveler's clock only slows for those who can travel near light's speed, and reaching that speed remains as impossible as ever. The shrinking of felt time is real, but it can only be claimed by a traveler who could never set out in the first place. The second count is what waits at the far end. While the traveler ages by decades, the universe ages by millions or billions of years. Everyone they ever knew is long gone before the journey is half done. The world they left has aged beyond recognition or ceased to exist altogether. The traveler might feel young at journey's end, but they arrive into a cosmos grown impossibly old, where the stars they set out beneath have died and been replaced, and nothing they remember remains. The clock that stays young for the traveler buys that youth at the cost of everything left behind. And the third count is the one that cannot be argued with at all. No slowing of the traveler's clock can enlarge the reachable universe. The cosmic event horizon does not care how time feels to the traveler. A galaxy beyond that horizon is unreachable, no matter how slowly the traveler's clock runs, because the space itself is growing faster than any ship can close, and no amount of felt time compression can overtake a gulf that widens faster than light. The traveler's clock can shorten the felt journey to the reachable galaxies, but it cannot open a single one of the unreachable ones. The loophole shrinks the time, but never the distance that matters. Late in the journey, it helps to gather the numbers softly into one place, not as a lesson, but as a slow counting, the way distances might be recited at the end of a long walk. The figures have been met, one at a time, each on its own rung, and set side by side, they trace the whole shape of the answer. There is a quiet pleasure in hearing them together, the small numbers and the enormous ones, laid end to end from the nearest star to the edge of everything. At the speed of our fastest machine, the swiftest thing human hands have ever built, the nearest star lies about 6,600 years away. The width of our own galaxy is about 160 million years across at that speed. The nearest great galaxy, Andromeda, lies some 4 billion years off, a journey longer than the age of the Earth. And the full breadth of the observable universe, at that same record speed, would take on the order of 100 trillion years, a span thousands of times longer than the universe has yet existed. At the speed of light itself, the floor beneath all crossing times, the numbers shrink but stay enormous. The galaxy is crossed in 100,000 years. Andromeda is reached in 2.5 million. The bound island of the local group is 10 million years across. The nearest great cluster lies 50 to 65 million years away, and a supercluster more than 500 million. And the whole observable universe, even at light's own speed, would take about 93 billion years to cross, nearly 7 times the present age of the universe. And then there is the figure that is not a figure at all, the one that replaces a number with a simple impossibility. Once the growing of space is taken into account, most of the universe cannot be crossed in any time whatsoever. About 94% of the galaxies we can see lie forever beyond the cosmic event horizon, unreachable by anything, at any speed, sealed away by a gulf that widens faster than light. For the great majority of the universe, the honest crossing time is not a span of years, however long. It is simply never. Set in a row, the numbers tell a single story. At our real speeds, the universe is uncrossable in any meaningful span. At the speed of light, it is still uncrossable in less time than the universe has existed. And with the expansion included, most of it is uncrossable at all, by anything, ever. The reachable part is a small bubble, our own bound group of galaxies, and even that bubble is slowly contracting as the far galaxies slip away. The arithmetic, gathered in one place, points everywhere to the same quiet conclusion. The conclusion is worth stating plainly, because it is the true answer to the question the night began with. The limit on crossing the universe is not a limit of engineering, or ambition, or patience. It is not that we have not yet built a fast enough ship, or gathered enough resolve. The limit is written into the structure of space and time themselves. There is no speed that opens the far reaches, no machine that closes the gulf, no span of waiting that brings the distant galaxies within reach. They are closed not by difficulty, but by the shape of the cosmos. And that fact, rightly understood, turns out to be less a wall than a kind of rest, which is where the journey finally turns. There is a gentler way to understand all of this, and it comes from noticing a quiet assumption hidden in the question itself. To ask how long it takes to cross something is to assume that the something is a place, with a near side and a far side, and that the far side waits to be reached. A hallway has a far end. A field has a far edge. An ocean has a far shore. A galaxy, for all its size, has a far rim. Each of these is a place, and a place can in principle be crossed, because it has another side that stays still and waits for the traveler to arrive. The universe is not like this, and that is the deepest reason it cannot be crossed. The observable universe is not a place with edges standing somewhere out in the dark. It is a horizon centered on the observer, reaching the same distance in every direction and receding outward everywhere at once. There is no far side holding still and waiting. There is no other shore. The question of how long it takes to cross the universe quietly assumes a destination that the universe simply does not provide. The far edge is not a place one could stand. It is the limit of sight, and it moves. To be inside the universe, then, is not to be inside a container that could be traversed from one wall to the other. It is to sit at the center of a sphere of old light, with more universe arriving from the past in every direction, and the farthest reaches forever sliding away. Wherever a traveler went, they would find themselves still at the center of their own horizon, with the same enormous distances stretching away on every side, the same edge receding as they approached. One cannot reach the edge of the universe any more than one can reach the horizon at sea by walking toward it. The horizon simply keeps its distance. This is why the unreachable majority of the universe is not a failure of any kind. It is not that we have fallen short of a journey we might have made. It is that the journey was never the sort of thing that could be completed because the universe is not a destination. The galaxies beyond the event horizon are not slipping from our grasp through any fault or weakness of ours. They were never within reach to begin with, and their quiet receding is simply what it means to live inside an expanding, light-limited cosmos. The closed far reaches are not a door shut against us. They are the shape of the space we happen to inhabit. Seen this way, the impossibility at the heart of the night softens into something almost peaceful. The universe cannot be crossed, but then it was never a road, never a sea, never a country with a far border to be reached. It is the condition we exist within, the medium in which everything we know is held. Asking to cross it is a little like asking to step outside the idea of distance itself. The wish dissolves not into disappointment, but into a kind of understanding, the recognition that we are not travelers stranded short of a destination, but inhabitants resting at the center of something that has no outside. And there is a comfort folded into this, that the journey has been moving toward from the beginning. The same enormous distance that makes the universe impossible to cross is the very thing that makes the night sky steady and calm. Because the stars and galaxies are so far away, and because we cannot race out to disturb them, they hold their places night after night, year after year, across a whole human life. The distance that forbids the journey is the distance that keeps the sky still. And that is the quiet truth the night comes to rest upon, the thought to carry down into sleep. And so the long journey comes to its quiet end, not at any far edge, but back here, beneath the same sky it began under. We set out to cross the universe, climbing the ladder of distance rung by rung, from the single light second to the moon, all the way to the 93 billion light-years that span the observable cosmos. We measured the climb against our fastest machines and against light itself, and we met the two walls that stand across the way. And we found, gently, that the universe cannot be crossed, that most of it lies forever beyond reach, sealed away by the slow and ceaseless growing of space. But the ending is not a sad one, and it was never meant to be. The far galaxies go on receding, sailing outward over a curve of space that widens behind them, and they ask nothing of us as they go. They do not need to be reached. They do not wait for us, or miss us, or call us outward. They simply drift in their immense slow patterns, glowing with light that left them long ago, indifferent and calm. We will never travel to them, and they are perfectly at peace without our ever having tried. There is nothing owed in either direction across all that distance. And because we will never reach them, they stay exactly where they are. The stars hold their places through the night. The faint patch of the nearest great galaxy hangs in the same quarter of the sky it has hung in for all of human memory. The slow wheel of the heavens turns with such enormous patience that across a single life it scarcely seems to change at all. The very distances that close the universe to any journey are the distances that keep the sky constant and quiet above every sleeping person. A steady ceiling of old light that asks for nothing and changes for no one. So there is nowhere you need to travel tonight. The journey across the universe is one that no one will ever make, and that is not a loss, but a release. You do not have to cross those distances. You do not have to reach those far shores. The universe has already done the only thing it asks of you, which is to hold the stars in their places while you rest beneath them, the same stars that have stood over every quiet night there has ever been. The far galaxies will keep their distance whether you watch them or not, and the keeping of that distance is its own kind of peace. Let the great reaches stay where they are then, scattered and faint and unreachable across the dark. Let the universe keep its far shores. There is no edge to be found tonight, no crossing to be made, nothing at all that requires your effort or your motion. The distance has settled the sky into stillness, and the stillness is yours to rest inside. Let your thoughts slow and grow soft. Let your breathing settle into something even and quiet. Let the weight of the day drift loose and fall away. The universe is enormous beyond crossing, and it holds you gently at its center, asking nothing, keeping the stars in place above you through the long and peaceful night. Let your eyes grow heavy. Let the far galaxies go on drifting in their slow and silent dark. There is nowhere to go and nothing to reach, only the quiet sky, holding still, and the soft return of sleep. Rest now. Sleep well, and good night.